Hello, so this is the next part of the additional maths video series. We're going to look at relative velocity. So here on the screen you see the syllabus section for vectors. This stuff, these bits of knowledge here, you should already know. They were discussed in P1, so Pure Mathematics 1 CIE A-level. How to write vectors, what's a position vector, what's a unit vector, magnitude, addition, subtraction, scalar multiplication, but what you haven't done yet is these two things here. Compose and resolve compose and resolve velocities is a bit of a strange one. I think they're talking about the resolving in directions v sine theta, v cos theta, which you would have done. Certainly you should have done a lot of that if you've studied mechanics at all. I'm afraid I only just noticed that line. It's a bit of a strange one, but don't worry about it. There's nothing different there. Now, relative velocity is what we're going to study today in this video. And it's quite a difficult topic. Don't want to scare anyone, but it's something that students struggle with, at least to begin with. And it may be one question on the exam, but if you're aiming for a high grade, you obviously can't afford to have any area that you're weak on. So even if it takes a long time, unfortunately, most students will have to spend that time in order to get good at this. Now, I'm going to start by maybe I'll just show you roughly what I'm going to do. It's going to be a fairly long video, I think, but let's see. First, the concept. What does relative velocity mean? How is this connected to vectors? How does it work in practical terms? So I'm going to show you just some examples of how it works in real life. Then simple examples, how it applies to swimming in a river or an aeroplane flying in the sky. And I'm going to show you a detailed example from my PowerPoint file that I use for teaching in the classroom, and then I'm going to show you probably 2 exam questions. Let's see how it goes, but I hope that by the end of this video you'll be able to solve a typical relative velocity question on the exam, but not, I must emphasize, not interception, which I'm going to cover in a separate video. As here it says, but not closest approach. Well, I'll explain that later. Okay, so that's what we're going to do. So first of all, the concept, the idea. Probably the easiest way to understand the idea is if you imagine travelling on a train. Not quite sure how best to draw this. It's going to be very rough. Sorry about that. Well, that's pretty bad, isn't it? Let me try that again. I can maybe how do I make a nice little box? Just come to think of it, I need quite a big box. So let me do this properly. So we'll make 2 lines. One day I'll figure out how to do this quickly, but for the moment I haven't figured that out. So there it is. So here's my train. Okay. So imagine it's a train. I know it doesn't look like a train. And imagine that the train has a speed. It's moving. It has a certain speed. Let's say its velocity or its speed is 15 meters per second. Okay. And of course people are on the train, including you, let's say. So let's say you're here and somebody else is sitting down over here. There they are. Okay, so suppose you've got up and you decided to go to the toilet or something, I don't know, and you decided to move. Well, you don't really decide these things, do you? But you're moving at a speed of 2 meters per second. Now, what does that really mean? You're moving at 2 meters per second. If you were really moving at 2 meters per second from the point of view of this guy over here standing outside the train, well then that means you would actually be flying backwards, wouldn't you? Because the train itself is moving at 15 meters per second. So if you're only moving at 2 meters per second, you're going slower than the train, so you're going backwards at 13 meters per second. But obviously that's not what we mean. So maybe we could draw this 15 meters per second here. The idea that you are travelling with the train speed. This guy is travelling at 15 meters per second. Let's give these guys names. So this is Mr. X, this is Mr. Y, and this is Mr. Z. So X is travelling at 15 meters per second because the train is. You're also you or Y, let's say Y is also travelling at 15 meters per second, but Y chooses to start walking. So his 2 meters per second adds together with the 15 meters per second of the train to give 17 meters per second. So all of this should be quite logical and common sense to you. Now notice what I'm talking about here is motion along a single line. Train, let's say, is moving along a line, not a curve. You imagine that's the line the train is moving along. Well, it makes it quite easy to understand relative velocity if we're working in one dimension. One line is one dimension. So in this case we can say that the velocity of y relative to x, and I'm going to write this using a certain notation, so velocity of y relative to x, so here this slash here is saying y relative to x is 2, because y is moving away from x at a speed of 2 meters per second, but the velocity of y relative to z, who's standing outside, let's show z's velocity of 0 meters per second. So the velocity of y relative to z is in fact 17 meters per second, isn't it? Because y is travelling at 2 meters per second inside the train carriage, but he's also travelling on the train, so we have to add the 15 to the 2. So this explains the concept of relative velocity. By the way, if you've ever thought about this, you should realize that all velocity is relative velocity. Yeah? If you think that you're not moving now, perhaps you're sitting in front of your computer and you're looking at this, you're thinking, I'm sitting still, I'm not moving, my velocity is 0. But of course that depends on the point of view of the person looking at you, right? If an astronaut in space was somehow looking at you, he might see you moving very fast because you're on the surface of the Earth, which is itself moving very quickly because it's rotating, spinning. If you were near to the Sun and in the rest frame of the Sun, if you were stationary with respect to the Sun, you would see the Earth moving very quickly because the Earth is revolving around the Sun. So any person on the Earth, even if they're not moving on their point on the Earth, they are moving relative to some other place in the universe. And indeed, we could ask a question like, going further with this idea of relative, look at y and z again. Here's y, here's z. What's the velocity of z relative to y? So this idea of relative to, let me put the words here. The velocity of z relative to y would be like imagining that y's velocity was 0. If y's velocity is 0, if y is at rest, then z is moving at a speed of 17 meters per second in this direction, isn't he? Yeah, to the left on this diagram. So the velocity of z relative to y would be minus 17 meters per second if we're taking this direction as positive to the right. Okay, so that's the idea. I don't want to spend too long on it because it's quite easy to understand, I think. That's not what makes this topic difficult. So let's look at another slightly more confusing example, still a simple example, but a slightly more confusing one, which does tend to cause problems when you're first looking at these questions. So let me just draw, again I need two horizontal lines. Let's try to get these flat. Okay, I'm going to make two of these again, but for a different reason this time. So here we're not thinking about a train, but we're thinking about a river. So imagine now we're looking at a river, and as you know, a river is a river because the water flows, the water moves. So maybe let's have some water. Oops, is that how water looks? I don't know. Little waves here. So we've got water in the river. Now the water's moving from left to right, and it will have a certain speed. Let's give it a speed of 3 meters per second. So that's the water's motion. Now let's say we want to swim across the river from point A to point B. So you're standing on the bank. You've decided that you want to go from A to B. How do you do it? If you swim with a forwards velocity, let's say a velocity perpendicular to the banks of the river, these are the banks. If you apply, as it were, a force on yourself to accelerate yourself, to move yourself from A to B, and somehow you create a velocity of, let's say, 3 meters per second in that direction, what will happen? What will be your path of travel? Will your path take you directly from A to B? Well, clearly not. The easiest way to understand it is imagine that instead of applying a speed of 3 meters per second, you applied a very small speed. Imagine you swim very, very slowly, maybe 0.01 meters per second. So what will happen in this case, because the water is travelling at 3 meters per second, yeah, maybe you travel at 0.01, something very close to 0. Well, of course, you're going to travel in this direction, aren't you? Sorry for that terrible diagonal there. Oops. You're going to travel in this direction because the water will carry you to the right. So if your speed is small or effectively 0, you will just travel to the right. You won't travel from A to B at all. Yeah. And if we go back to our original idea that you decided to travel from A to B with a speed 3, if you applied a speed 3 in the direction AB, well then let's think about what will happen to your motion. In every second you will go forwards 3 meters, but in every second you will also go to the right 3 meters. Because again, if you're in the water, then you're being carried with the water. So your direction of travel will end up being at a 45-degree angle. Yeah. So what will actually happen if you apply this is you won't go from A to B at all. You'll go to a point over here where this distance is equal to this distance AB. You'll end up, let's be specific, at a point C where AB equals BC. So in this case you will have failed to achieve your goal, as it were, of going from A to B. So then you realize, well, okay, if I need to go from A to B, I need to have a 0 velocity. So if your true velocity, let's put the guy Z is over here again, and your Y. So if you want Z to see you traveling in the direction AB, you need your true velocity to have 0 component in direction of river, let's say. So by direction of river I mean this horizontal direction on the diagram. Of course it's not really horizontal because this is a plan view, but you get the idea. So how can we have a zero velocity in the direction perpendicular to AB, in the direction of the river? Well, in order to have a zero velocity we have to fight the current, yeah? We have to fight the water. In order to fight the current we need to create a velocity to the left which balances out the velocity of the water. Okay, now and the more you think about this you realize it's a vector question, isn't it? Because what we're saying is that the velocity of the water, let's draw it as a vector. Sorry, if I'm drawing it as a vector I won't draw it as a velocity. Okay, so let's draw it as a normal vector diagram. And let's call that VW. The velocity of the water as a vector has magnitude 3 and it's in this direction. So if we want to go from A to B we have to add to this our own velocity. What am I going to do here? Maybe a blue colour. I need to add a velocity equal and opposite as well as a velocity in the direction of AB. So my velocity needs to be, so this will be the guy Y here, will have to be not equals, an arrow that looks like this. A component in this direction and a component in this direction, that gives a resultant velocity in that direction. So what I will need to do is to create a velocity which has, now it won't matter how fast I'm going in this direction, but I need to have a magnitude of 3 meters per second in this direction opposite to the water. So it might be, for example, this, that might be my velocity. Where this is a 3 meters per second magnitude, and this magnitude can be anything at all. Now, it's easy to get confused in these diagrams if you forget about the difference between velocity and displacement vectors. So when I drew, when I drew this arrow here, I was drawing a velocity arrow, which is a vector. I wasn't drawing a displacement arrow. So similarly here, these green arrows are supposed to represent velocities. So this 3 meters per second to the left will balance out this 3 meters per second to the right, and then the motion of the swimmer will be of y here, will just be directly from A to B. Okay, the purpose of that section was to give some physical explanation, but I'll keep sort of working on the physical explanation as we go on through the examples. But now we've got to be a bit more mathematical. We've got to actually write this as equations, in particular vector equations, to understand a bit better how we can use these, how we can calculate these things in real examples. So let's think of this as a vector equation. The velocity of let's say y, so here y is this guy, will be equal to the velocity of y relative to the water plus the velocity of the water. Now what does that mean? Do you see what I'm saying? Here the actual, let's annotate this equation. This is the true velocity, and it's often referred to as the true velocity because it's the velocity seen by somebody on the ground, or as it were outside the situation. So for example, here on the train the true velocity of y is 17 meters per second because z sees y as travelling at 17 meters per second. Now of course, as I said at the beginning, the idea of true velocity doesn't really make any sense because there is no absolute position from which all other velocities should be measured. But in practice what we really mean by saying true velocity is the velocity seen from the ground, from the Earth's surface. So here z, if we look at z is on the Earth's surface. He's not moving relative to the surface of the Earth. He sees the water moving, he sees y moving through the water, but he sees the true velocity of y as being this velocity directed from A to B, because that's actually how y will travel. He will travel from A to B. So that's what we mean by true velocity, as seen by z. I'll write here, and you should understand z means a person standing on the Earth's surface. Okay, so that's Vy. Now what's this one? Vy relative to Vy slash W means relative velocity. And that's the velocity of y relative to the water, just as I wrote up here, relative to. And here, this is the water's velocity. Now, another very important note about language. This one we've said is the relative velocity, but it has another name which is very confusing, but it's often used in exam questions. As well as being called relative velocity, it's sometimes called velocity, or occasionally speed if we mean magnitude, in still water. Now students find this very confusing. It's like a kind of code, you know, it's almost impossible to understand it without being told. So here still means zero speed or zero velocity, same thing. So what on earth does this mean? The relative velocity is the velocity in still water. Well, it's easy to understand physically. Look at the green arrows here. What we said was that in order to get from A to B, we have to direct our velocity in this direction, so to cancel out the water's velocity. Now imagine the water's velocity was 0. If the water's velocity is 0, then we would simply have to travel. We would simply just direct no, what I'm saying, sorry. If the water's velocity was 0 and we applied the same velocity, this green arrow here, as our velocity, then of course we would just travel along this line, wouldn't we? If the water weren't moving. And so what that means is that this arrow here, this green arrow here, is the velocity in still water, isn't it? If there's no water velocity, that is our velocity. That's our true velocity. Yeah. So another way to say it is, if this is 0 on the equation, if VW is 0, then Vy equals Vy slash W. Yeah. So that's what we mean by velocity or speed in still water. So that is often used. Now let's not forget that we're talking about vectors here. I forgot actually to underline them. This is a vector, this is a vector, and this is a vector. So this is a vector equation, so it can be written as... now let's apply this equation to this scenario. Look at the green arrows. Look at the 3 parts of the green arrow. Hold on a minute. Which way round is it? Okay, that's the relative. Okay. Sorry, what am I trying? Oh, I see. Yes. So this is the true velocity. This is Vy, isn't it? This is actually how y is travelling. And this longer arrow here, this diagonal vector, is the velocity of y relative to the water. And this arrow, which I'm drawing in the other direction, is the velocity of the water. So let's think about this again. Starting from this vertex here, if we travel here, Vy slash W, the velocity of y relative to the water, plus the velocity of the water, leads us to the vector Vy, which is the true velocity of y. And again, what is the true velocity? It's what z sees. Z is sitting on the side of the bank. So I guess that explains the basic principle. It is confusing, so I'm hoping that extra explanation helped you. to emphasize why is the idea of velocity or speed in still water important. It is important because suppose you're a championship swimmer, suppose you're an Olympic swimmer, and you can swim very fast. You know, you can swim at, what's a fast speed to swim at? I don't know, 10 meters per second. I'm just guessing. So suppose you can swim at 10 meters per second. Well, of course, what that really means is you have the ability to move through water at 10 meters per second. But in a real river, you can travel much faster than that, can't you? Because, for example, if you decided to swim with the current, so this is the current to the right, if you decided to swim in the same direction, then the water speed will be added to your speed, so you'd be 10 plus 3, 13 meters per second. If you decided to swim in the direction opposite to the current, then obviously you can't swim faster than 7 meters per second. And if indeed you want to travel from A to B, then your speed in still water is still, which is this one here. Yeah. Your speed in still water is this one here. It's your velocity relative to the water. And if you can travel at 10 meters per second, it means the magnitude of this vector, the size of this vector, can be 10. The size of this vector and this vector can be anything at all. So that's why in practice this idea of speed in still water is actually very important. Okay, so what we're going to do next is look at a more detailed example, but this time it will be an aeroplane flying in the air. And I'm going to use my PowerPoint file for this, so just bear with me. I need to press that, I think. Okay. Okay, so relative velocity here. I'm got a little explanation of a little explanation of resolving. We're going to use that in a minute. You should know that already. V cos theta is this component, V sine theta is this component. Now here, notice that my notation is a bit different. This means velocity of B relative to A. That reminds me, I should come back and show you that on the notes. We wrote this equation. This is the relative velocity equation here. Now, of course, it can be written in a different way, and I think it's a more easy to remember way. Velocity of y relative to w, to water, is equal to the velocity of y minus the velocity of the water. Yeah. So this is the standard relative velocity equation, which you should understand in terms of a triangle like this. Yeah. A vector addition or subtraction triangle. So that's what we're seeing on the PowerPoint here. And just get back to that. You can also put the B to the left of the V here. So velocity of B, it says here, relative to A is the velocity of B minus the velocity of A. But that's a vector equation. Okay. Now then, we're going to look at an example where there's a plane flying from London to New York. So the numbers here I just made up. They're probably not very realistic, but they give you the idea. So we've got the distance from London to New York. It's a certain distance, 5,600 kilometers. And we've got the air. Here I'm using A for air, but you can think of it as wind. Yeah. So the velocity of the wind is given. It has a magnitude of 120, and that will be measured in kilometers per hour, I think. Oh, here's the data. So plane flies directly west. Now we're assuming that London to New York is directly west, to keep it simple. Of course, that's not actually true, but we're just trying to make the maths a bit easier. And we'll call the distance 5,600 kilometers. Now, read carefully. Maximum speed of the plane through still air is this. I remind you, speed in still water. This is the same idea. The speed in still air of the plane is 950 kilometers per hour. What that's actually telling you is the relative speed of the plane, the speed of the plane relative to the air. The wind speed is 120 kilometers per hour. The bearing is 20 degrees. That means that the angle between direct north and the direction of the plane shown here, that's an angle of 20 degrees. Yeah, so that's the angle taken clockwise from the direct north direction. And we asked, how quickly can it reach New York, and at what bearing does the plane fly relative to the air? So again, bearing is the angle from north. So they're asking here, how quickly, what time does it take, and also what's the angle, the direction of the plane. So you can try and answer that on your own if you want. I'm going to show you my answer now in detail. So first thing is what? We're going to use the relative velocity of the relative velocity equation. I can't actually remember why I used d there. So here Vp would be the velocity of the plane, and Vd should be the relative velocity. I can't remember why it's d. I would prefer to write Vp/a, or velocity of plane relative to air plus the velocity of the air. So here we see it as a triangle. Now we know the velocity of the air, we know its magnitude, 120, and we know its direction as a 20-degree bearing from north. And we also know the direction of the velocity of the plane because we were told that the direction from London to New York is directly west. So that means we already know this direction, but we don't know its magnitude. To find out how long the plane takes to get from London to New York, we're going to have to find out the magnitude of this velocity vector, then use the velocity equals distance divided by time to find the time. Now here, this is again the relative velocity of the plane relative to the air. I still can't remember why it's called d. Vd, velocity of... Nope, can't remember why it's d. Sorry about that. Okay, we'll get on to that. So the velocity of the plane relative to the air is the true velocity of the plane minus the velocity of the air. Here we are, there we go. So velocity of plane relative to air equals velocity of plane minus velocity of air. Remember, a vector equation. And here I'm just going to have a side example here. This example we've already looked at. It's the same for a boat. The boat's direction in the water must be towards the left, opposing the water, if we want to travel directly from one side to the other. So back to this example. We have this vector, both in size and direction, but we take now two components. Now this is only one way to do it, I want to emphasize. If I want to find the length of this side of this velocity triangle, I could use, for example, the sine rule. But I'm trying to show you here a method which is very you can use it in any situation, which is to break the vectors into components. So on this triangle, this side is north south. This side is east west. So VA sine 20 is the component of the velocity of the air to the east, and VA cos 20 is the component of the velocity of the air towards the north. So it's written here, the north component, 120 cos 20, because the length of this red arrow is 120. And 120 sine 20 is the other component, to the west. Now the aircraft must travel due west. So what is here, d should be PA, yeah? This is the relative velocity. What is the velocity, in other words, what's the component of this vector VPA towards the west? It must be the same, minus 120 cos 20. So this here is the component of the velocity of the air to the east. This is the component of the velocity of the plane relative to the air to the west, so that there is a sorry, to the south. Sorry, this velocity vector must have a component directly south of 120 cos 20 to cancel out this, which is north, so that the plane's true velocity is only west and not going up or going down, not going north, not going south. And we continue the calculation. we know that the magnitude of this vector here, this arrow, is 950 because we were told that the maximum speed in still air is 950, and if we want to get there as fast as possible we use the maximum possible speed. So the length of this side of the triangle is 950, so we can draw that vector having two components. We know that this one here is 120 cos 20, we just proved that. We know that this one here has length 950, so we can work out the length of this one. So that the west component of this vector is the square root of 950 squared minus 120 cos 20 squared. That gives 943.3. Okay, and that component there, we must also take into account the fact that so let's be clear. This number that we've calculated here is the length or magnitude of this velocity vector, but that is not the true velocity of the plane. That is the component of the velocity of the plane relative to the air in the westerly direction. In order to find, so if you looked at this triangle, it would be this length from here all the way to the perpendicular there. But we also have to consider the velocity of the air. We're going to have to subtract that to get the right answer. We can also use IJ notation. This is very useful sometimes. If you're dealing with problems with directions north, south, east, west, assume that I is 1 unit to the east and J is 1 unit to the west. Then applying what we've just learned, we see that velocity of the plane relative to the air is 943.3 I. That was the easterly, that should be minus, sorry, that should actually be minus 943 I, yeah, because oh no, I'm sorry, it says here I is in the west direction, so that's a bit confusing, but it means I is moving to the left, so we do have 943.3 I, and minus 120 cos 20 J, that's downwards here, and the velocity of the air is simpler, it's just minus 120 sine 20 I, plus 120 cos 20j. So if we want to find the length of this arrow, we can use the relative velocity equation. The velocity of the plane is equal to the velocity of the air plus the velocity of the plane relative to the air. So if we add these two together, we see that, of course, this and this cancel out, and we're left with only a velocity in the west direction, and its magnitude is 943.3 minus 120 sine 20, and that gives us 902.2, and that's measured in kilometers per hour. So to find the time, we just divide the distance by the speed. Here the speed is actually to the west, and that gives us 6.21 measured in hours, because our units were kilometers and hours everywhere. So that's how we found the time it takes for the journey. We should also check the direction to get the bearing. Actually, we want to find the bearing of the plane. In other words, this is, as it were, the course that the pilot should set. Just like when you're swimming in the river, you're going to have to direct yourself to the left to counterbalance the water going to the right. What direction should the pilot set as his course? Well, we can work out this angle quite easily because we know we know the components of this vector in the north and west directions. Just divide them and take inverse tangent, it gives us an angle. Now that angle is not the bearing, because the bearing is the angle taken clockwise from the north, so we just go 180 plus, what's that, 90 minus that angle. Yeah, 180 plus 90 minus the angle gives us 263.2 degrees. And bearings, by the way, are always quoted to 1 decimal place of angles. So that's it. That's how you do it. I won't show you this example right now. I think what I'll do is show you at least one exam question and then see how we get on. Okay, so I should say that if you found that example a bit confusing, you would probably find it a bit easier to understand using a more normal geometry or trigonometry approach. If I drew it like this, there we go, so this was the air velocity, this was the velocity of the plane relative to the air, and this was the velocity of the true velocity of the plane. Okay, so this relative velocity, of course, is also called the speed, the velocity in still air. Now, if you remember what we knew in the question, we knew the magnitude and direction of this vector. This angle was 20 degrees. We knew the length of this was 120. We knew that the length of this line was 950, and we knew that the direction of this line was due west. So you can see that since you know this direction and this direction, that means you know that this whole angle theta is 90 plus 20 or 110 degrees. You know this is 950, you know this is 120, and that's enough information using the sine rule or the cosine rule. Let's say, I guess we want the cosine rule. Yeah, the cosine rule will tell us that if this is, let's give these names, like if this length is x, this length is y, and this length is z, we can say that z squared is x squared plus y squared minus 2xy cos theta. Excuse my handwriting. And that means that since we know everything in that equation except x, we get 950 squared equals x squared plus 120 squared minus 240x cosine 110 degrees. And this will give us the value of x. And that is in fact a slightly neater way to solve that problem. Because remember, if we know x, then we know the speed, the true speed of the plane, and then we can use time as distance divided by velocity to find the time taken. So yeah, that is a neater way to do the question, but the reason I showed it, the method using I and j, is because that method is more sort of powerful in the general case. But okay, I hope that helps, and if you found that example difficult, don't worry, I would consider that normal. It's a little difficult at first. Now we're going to look at two exam questions that illustrate the same kind of ideas. So let's start with this one here. A cyclist travelling due south, so that means you have the direction of the true velocity of the cyclist. He is actually travelling due south. Let's draw an arrow pointing south. True velocity of the cyclist. He is travelling a straight horizontal road. His speed is 7 meters per second, so the magnitude of VC is 7. The wind appears. Now that word is very important. Appears. What does it mean? It means the wind appears to be blowing from the northeast. So that's the velocity of I've forgotten actually what does we'll come back to that in a minute. Given that the wind has a constant speed, so the speed of the wind is 12, find the direction from which the wind is blowing. So we're going to use the speed of the cyclist. The true speed of the cyclist is the speed of the cyclist relative to the air plus the speed of the air. Sorry, this is velocities, not speeds. Okay, I've remembered why this word appears is so important and how to use it here. So the word appears here actually means relative velocity. So it's something to remember when you look at these exam questions, is when you see appears, it means this is how it looks to someone, which means it's relative. Now one of the things, and there's more than one thing, that makes this question a bit unusual, is what they're saying here is when they say the wind appears to be blowing from the northeast, is that they're talking about the speed of the wind relative to the cyclist. So actually, although this is correct, and you could solve the question that way, it's easier to understand to write it the other way around. The velocity of the air is the velocity of the air relative to the cyclist plus the velocity of the cyclist. And the reason I prefer writing it in this form is because that, in this form, the second term in that equation is actually what they mean by this phrase. The wind appears to be blowing from the northeast. They're talking about this velocity here, the velocity of the air or wind relative to the cyclist. So we know the direction of that vector, but notice, very, very tricky point, from. It's blowing from the northeast, so from northeast means its actual direction is to the southwest. Okay, so I'm actually going to remove this triangle that I drew here. And I'll try and show you how you can construct the correct triangle. That's the key to getting this right. Now, given that the wind has a constant speed, so we know the magnitude of the true speed of the wind is 12, we're going to find the direction from which the true speed is coming of the wind. So let's think about this. We know VC. VC is the velocity of the cyclist. That has a magnitude 7, and its direction is due south. Now, the direction of the we don't know the direction from which the wind is blowing. That's what we're trying to find, but we know its length is 12, and we know that this vector VA is the sum of this vector, which is the velocity of the cyclist, plus the velocity of the air relative to the cyclist, and we know that that velocity has a direction to the southwest. So look carefully. What I'm doing here is the velocity of the air relative to the cyclist. Yeah, that's right. So here, this vector is showing me the velocity of the air relative to the cyclist, and I know, if I draw a dotted line here, I know this angle, let me identify here, this angle is 45 degrees. Do you see that? Because this is the north direction, this is the south direction, so southwest is at an angle 45 degrees to that line. So that angle is 45 degrees. Now I'm going to draw another dotted line here. And to complete the vector triangle, I know that VAC plus VC is equal to VA according to this equation. So VA is the third side of this triangle, VA. And I also know that the magnitude of VA is 12. How do I write this clearly? So this is a velocity triangle. Here's VC, here's VA on the right. These dotted lines are supposed to run north-south, so they're supposed to be vertical lines. Yeah. And let's convert that to a simpler diagram, which is just geometrical. So now I have these three sides of a triangle. And what do I know? I know this length is 12. That's the speed of the wind. I know this length is 7. That's the speed of the cyclist. And because I know that this angle is 45, that means I know that this angle is 180 minus 45, or 135 degrees. So you see I have two sides of the triangle, and I have an angle. So in principle I can work out whatever I want to work out. But let's keep this as simple as possible. What we actually want to know is very simply the direction. This is a north direction here. We want to know the direction of this line here, because that's what the question is asking. So to find the direction of this line, what I want is the bearing of that vector. There's north again. I want to know the bearing of this vector. So I'm going to write here theta. This angle is the bearing of that vector. So to find that angle, the simplest way to do it, I think, you'll agree with me if you think carefully, is to find this angle here. there's just not quite enough room, is it? I'm going to actually try and use a much larger diagram. Large diagrams are always a good thing. Let me just rearrange my space here, put this up here, remove this, and I'll try and make it reasonably neat this time. So first of all, here's the cyclist velocity. Its magnitude is 7, and then I'll draw the this one here. This is the speed of the air relative to the cyclist, okay, or the velocity rather, and then we'll draw as best we can the velocity of the air. That's the undo that. That's the velocity of the air. Okay. So carefully annotating, we had a 135 degree angle here. Let's call this angle alpha, and let's just draw a north direction there and a parallel north direction there, and we'll call this angle theta, which is the angle we want. So how do we get this angle? There's no need to use the cosine rule, because here we just want an angle and we already have two sides in an angle, so we use the sine rule, and it tells us that 12 over sine 135 degrees is 7 over sine alpha. Because you can see that if you have alpha, it's going to be quite easy, because this angle here was 45, which means that this angle is 45, which means alpha is 45, or rather theta is 180 plus 45 minus alpha. Okay, so if you work that out, you're going to get, I'll just jump a step here. Actually, alpha comes to, I think, 24.36 degrees. So theta is actually 200.6 degrees, and that it might be natural to think that you've now found the answer, that this is the bearing of this vector. But unfortunately, the question tricks you even more, because right at the end it says find the direction, not the direction of the wind, but find the direction from which the wind is blowing. Well, the direction from which the wind is blowing is the opposite direction. Just as here, from northeast means to southwest. So the bearing is actually the opposite direction to this, which is 200.6 minus 180, which is 20.6 degrees, and that's the actual final answer. It's a very tricky question, so again, if you tried it and you got confused, don't be surprised. Now, I hope this second one is not quite so tricky, but it uses again the same ideas. So now let's see. We're going to have a river. The river's speed, the water speed, is 3 meters per second. The banks of the river are 200 meters apart, so let's draw this again. And we'll make a copy of that. Okay, so there's the banks of the river, 200 meters apart. Let's draw the 200 meters. And the speed of the water is 3 meters per second. The motorboat has a top speed of 6 meters per second in still water. There we go, still water. That means relative velocity, as we said. So let's write that now. The velocity of the boat relative to the water has a magnitude of 6. And we're going to travel from point A on one bank to point B on the other bank 150 meters downstream. So downstream, of course, means in the direction of the water. So I'm going to construct a triangle here where one side is 200 meters and the other side is 150 meters. That's what is meant by this 150 meters downstream. Assuming the motorboat is travelling at top speed, which is that 6, find the time it takes to travel from A to B. Right, well what this is telling me is that if I'm going to travel from A to B in this boat, I need my velocity vector to point in this direction. Now what is this direction? It's easy to figure out because we can say tan theta is 3/4. So we know the angle there of the velocity vector. Now that will be the direction of the true velocity. So let's write the relative velocity equation. The velocity of the boat is equal to the velocity of the boat relative to the water plus the velocity of the water, and the velocity of the water we know is 3, or its speed is 3, and its direction is this direction here. So it should be pretty easy to figure out the triangle. The triangle will look something like this. Velocity of the boat relative to the water plus the velocity of the water is equal to the velocity of the boat. Oops, maybe I'll just join those up there, and this angle, difficult to draw, isn't it? This maybe I can just do it this way. Again, same lesson we always learn. The bigger the diagram is, the better it will look. Let's draw. Which way to do this? Let's draw a big line starting here, like that. That's not bad, is it? And another one like that. Yeah, that's a bit better. Maybe this will work okay. Okay, that's good. And we'll draw one more line. Whoops, one more line here. Okay, so that's the velocity of the water, and that will have magnitude 3. Magnitude of that is 3. This is the true velocity of the boat, and the velocity of the boat relative to the water must have magnitude 6. So we've got two sides, 6 and 3, and we've got an angle here. I think I'll do the opposite angle. So if this is theta, this is 90 minus theta. So that's 90 minus theta. And let's just remind ourselves what we're trying to find out. We're trying to find out the time it takes, which means we need the magnitude of VB. So this should be quite easy. What's the quickest way? Let me think. Oh, of course, this is also 90 minus theta here. Maybe we should just work out theta. Well, there's no need. This is 90 minus theta. So I want the length of that side. Probably the cosine rule should be nice and simple. Hold on, what's the quickest way? So in a problem like this, you can see that you have enough information in the triangle. You have one angle, you have two sides. So you can work out anything you need to work out about this triangle. The most important thing is just to make sure that the make sure that you're a bit careful about using the sine rule, because two different angles have the same sine. So you must be careful that the structure of your triangle makes sense. Sorry, I'm slightly forgetting what I'm trying to do. VB here is what we're trying to find the length of that side. Okay, now do we know? Okay, let me just write it in terms of the cosine rule, and maybe there's a quicker way, but this should be fine. So 6. I'm just trying to find an easy way, because if I can use this angle, the cosine rule will be much simpler. This is a 90 degree That's 90. Okay, that's the true velocity. Okay, sorry for the hesitation here, but what I'm hesitating about is that I can see this calculation is going to be a bit messy, but I just double checked and there aren't really any clever ways to do it. You just have to do it. So what you have to do here is find the value of the magnitude of VB. So I'm going to give that a name to make it less confusing. Let's say the length of that vector is x. Then using the cosine rule we're going to get this formula. So the opposite side to the angle is 6, so 6 squared equals 3 squared, that's this length here, plus x squared minus 2 times 3 times x times the cosine of this angle. Now this is 90 minus theta, so the cosine of that is the sine of theta, and the sine of theta, looking here, you see is 3 over 5, so I get 3 over 5 here. So this simplifies, well, it doesn't simplify, that's the problem, into a quadratic equation in x. So there'll be two answers, but only one of them will be physically true. Let me just get rid of this stuff here. Just going to get in the way. So we're going to solve this quadratic. That's a bit messy, but it's okay with a calculator. So you'll get, if you simplify this down, you get 5x squared minus 18x minus 135 equals 0. So the 135 is here 9 minus 36, that's minus 27, and then multiplied by 5. Okay, so this doesn't factor easily, but if you try and solve it, you'll get x using the formula. You'll get 1.8 plus or minus about 5.5. So there's only one positive answer, and the speed must be positive, so that will be 7.3 approximately. Let's say approximately 7.3. Now that's the speed, true speed, of the boat. Okay, so just to review what we've figured out, the boat travels from A to B. We've figured out its true velocity, VB here, has a magnitude of about 7.3. So since we want to find the time, we're just going to use time as distance over velocity. Now the distance is the distance AB, so the distance AB is easy to see because this is a 3, 4, 5 triangle, so that's 250 meters. So the time is 250 meters divided by 7.3. Forget how many seconds that is, maybe 34 seconds. Anyway, so you can check that. So that's how to do these kind of problems. You can see they are really quite tricky in terms of not just the concept, but also you have to read the words very carefully. Now I'd like to emphasize here that again, I think I said this once, but please be careful when figuring out the angles in these triangles. It would be instructive, for example, here to wonder what would it look like if the how can I say? Well, for example, it might be the case that the direction of the boat's relative velocity would be to the left, and would that make any difference? In other words, if the triangle looked like this instead of like this, would that make any difference to the calculations? So in some cases it doesn't matter, but the important point is that the sine of 180 minus theta is equal to the sine of theta. So there are two different angles with the same sine, which means that if you use the sine rule, you have to be very careful that you know which of these two cases is correct. I would say in most questions this is not a problem, but occasionally it will be, so do be careful about that. Okay, in the next video we'll talk about interception problems, which are connected but not the same. So thanks, see you next time.